All right then. I think we had a good question from Johanna just before the break, which is a perfect starting point for this presentation here. This presentation is about alternative district heating concepts, renewable concepts, of course, and applying the QM system for these concepts. Oh, sorry. Yeah, now it's working. So Johanna mentioned already that in future district heating systems, renewable district heating systems might look a bit different, so that we do not have these classical biomass district heating systems as we were talking about before. I think it's clear that we have to use renewable heating in future, renewable district heating, of course. I hope we do not have to discuss about that. I just want to mention here that in the past there was sometimes a discussion about which renewable is the best, which should we use. This rivalry between technologies is totally useless from my point of view. So I think we need all we can get to face the challenges or to cope with the challenges we have with our climate change. District heating, this is from my point of view, a very, very important message. District heating is a valuable infrastructure to collect and utilize every local available renewable heat source, best possible in the most efficient way. For Austria, we have a great infrastructure. We have more than 2,400 biomass district heating systems, and we see that they are opening up, that they are starting to change, that they include new heat sources, that they increase their efficiency, and that they will change. So the change has already started. We see a lot of new, totally new technologies in district heating coming up, new concepts in different countries, from very low temperatures to different hydraulic concepts. So a lot of things are going on. Existing district heating is a perfect starting point, of course, and new projects, this is very important, should consider all potential sources. So open up, do not think about biomass alone. Biomass is a good starting point, is a well-proven technology, but as soon as you think about a renewable district heating system in your area, open up and consider everything you have. Here are some ideas on how to prioritize your search regarding available heat sources. We have that in our planning guideline annexes about flexible district heating. So just an idea on how you can proceed with that. Location-bound sources are of higher priority than other ones, which you can transport, of course, because you can just use in your area and nowhere else. Non-resource consuming, non-emissive sources, which will not include biomass, to be honest. We have emissions in biomass. We want to reduce them, as we learned before, of course. But these are the main things you should consider and set your priorities during your evaluation of the area and the assessment of heat sources. Sources with high temperature levels, of course, they are more valuable than other ones, but we need the other ones as well. Is it possible to integrate them effectively? This is what we will go in a bit more deep afterwards. This is where the question of Johanna is related to, is going to. Does it fit in with various parameters? How about transport, storage ability, things like that, positive, negative interactions with other heat sources, with the overall system? And are there any obstacles which we cannot cope with? This is some idea how you can start in the very beginning. As I mentioned, we have prepared planning guidelines and some annexes to these planning guidelines, so the short version of planning guidelines. One of these annexes is our flexible DH solutions, where you can find a lot of information about that. What we have to consider is that these systems are not easy anymore. We just learned that it's already quite complex to get a nicely designed, high efficient, low emission biomass district heating plant. But considering multiple heat sources, various other characteristics of these heat sources lead to much more complexity in the system. This is very clear. We have distributed heat sources. We might have prosumer solutions. We might have total different technical concepts, coupled with classical concepts maybe, reduced system temperatures, multi-level temperature systems, sector coupling, short, long-term storage. The intelligent control strategies hopefully help us to cope with all that. But of course, before we do so, we need a proper designing and planning of these systems. Comprehensive and detailed planning is even more important. We already mentioned, Christian showed us 70% of the costs are defined during the planning phase, not with the procurement, as many people think, not with the investment costs alone. They are defined during the planning phase. And with these more complex systems, it's even more important to have a high focus on planning, strictly definition of tasks and responsibilities. We might have even more interfaces between units in the systems. And QM includes all of that, to be honest. Maybe not that we are coping with that kind of systems yet in terms of benchmarks, of technical requirements, but QM offers a very nicely structured process to cope, to ensure that you have a good planning procedure. So the QM process itself is very valuable even for that kind of systems. We will learn about some about the things with benchmarks and quality criteria, which is a bit tricky for such complex systems. I mentioned where you can find it. I added one slide to mention it, that you should a little bit start thinking beyond heat, especially for newly designed systems, but for existing systems as well. So these new renewable district heating systems, we have existing examples, but there will much more coming in future. They're sometimes thinking beyond heat. So there is great potential to use a local district heating systems to trigger new additional projects, ideas. We saw that in Austria. We have operators operating as internet provider as well. We have shared infrastructure. I mentioned sector coupling. You can do sector coupling on your own, start producing electricity with PV. CHP is a well-known concept. You have to take care a little bit here. You can even start doing a local power grid. So there are many ideas. Not all of them might prove to be the best ones in future. So it's not that I want to suggest all of this, but start thinking. This is very important. Citizen participation models could be a nice way of financing your projects. Energy communities, fuel trading with biomass, that's well known. We have car sharing together with biomass district heating as well. So there are synergies you might use. So these new concepts allow a better thinking, a widely holistic concept integration of many other things. But we have to keep in mind that QM is made for these classical biomass district heating systems. For woody fuels, starting from 100 kilowatts upwards, usually applied for local district heating systems. This is where QM comes from. We have some limitations of the system, or especially the quality criteria, the benchmarks we use. So we have to think about that. QM generally does not forbid any other heat source. This is very clear. We always included that. You always can include another heat source. It does not have to be an oil and gas boiler, as we mentioned before. So you can have any other heat source. It's not defined directly. The thing is, you should still stick to the basic idea of QM. The plant configuration must ensure that the boilers are operated in the way they are designed for. And this is valid for all other heat sources as well. So this has to be assured for the biomass boilers. There it is very important, the dimensioning and the operation, because it's a costly plant component, but it has to be ensured for all other heat sources as well. They have to be operated within their design criteria to guarantee low emissions, high efficiency, and high durability of the plant components. So the basic idea is more or less the same. This means the general requirements do not change for the overall planning process. I mentioned that we have a good structured process. We still need a very high precision heat demand assessment. We need a proper system selection, which is much more complex, of course. For the district heating network, you can use the same requirements and quality criteria we had already. In case you have very special concepts, they might change a little bit, but the basic idea is the same. We want to have low investment costs, high utilization of our investment costs for the district heating system, meaning high linear heat density. Even though if very new systems with low system temperatures might have less heat losses, but you still have investment. So linear heat density is still an important benchmarks. And of course, I mentioned it, the heat losses. Low bumping power demand. So it's the same criteria here. Monitoring and optimization, a very integral part of the QM process, can be applied here the same way, completely the same way. General considerations regarding biomass boilers, this is clear, and use QM likewise. That's how I say it. We added one slide here to show where you can find what. Within the ENTRAIN project, we prepared planning guidelines. This is a very short, compressed version to give you a good overview as an energy agency, as an information for mayors, project developers. They are not going into the detail. These planning guidelines include some annexes for heat pumps, for thermal solar, for waste heat, and for general overview of flexible district heating solutions. So there you get a very good overview. And upcoming, as I mentioned, is the new QM planning handbook. And this includes now more information about new concepts, always related to biomass district heating, of course, to be honest. But so we always have biomass boilers in interaction with heat recovery, with heat pumps, with waste heat integration. We have multi-boiler plants. So this is a significant enlargement of the QM system, of the knowledge basis of QM within this planning handbook. As I said, this is upcoming. Translation is almost finished for the English version. This is just one example of what you will find in the new QM planning handbook. So we have additional standard hydraulic schemes with basic design criteria, basic ideas behind these criteria. But I have to mention that these concepts are so complex and that there are so many options of integrating a condensation unit, for example, a condensation unit with a heat pump, so an active condensation unit. that it is not possible anymore to to stick to a very few standard hydraulic schemes. So here we have to be more open-minded to be able to allow these solutions to develop and to be integrated. And to be honest, if we start talking about systems like this, what we see here, or integrating waste heat sources, thermal solar plants, other things, it is very, very clear that you need expert planners. You really need expert planners. This is these are no simple heating plants anymore. This is not comparable to a standard standalone heating plant of a single family home. So this is not out of the box planning. You need a tailor-made concept, and this is the reason why QM has to stop at a certain point to go into very detail with quality criteria or design concepts. Due to the complexity and due to the number of options you have here. This is always related to the overall system concepts, the various heat sources, and then you get tailor-made overall concepts. But as I mentioned before, use QM likewise. Take into account the basic idea of QM that every production unit has to be operated within its design criteria, that you get overall high efficiency and low emissions of the plant, that you have high flexibility, and it is very clear that you need a holistic control strategy of the overall system. This is just an example of what you find as well. So we go into more detail for some additional heat sources in the new planning handbook. This is an overview of the COP depending on the temperature difference of the heat pump. Of course, we know that there is a strong dependency on the efficiency of a heat pump to the temperatures they have to provide, or the temperature of the heat source. I think we don't have to go into more detail here. What I want to mention here is QM says something like COP of 4 for a compression heat pump as a benchmark. This you will find even in the new planning handbook. I'm a bit critical on that because there are different concepts. For a standard concept, the heat pump, you can say, okay, let's take a COP of 4 as a first benchmark. But there are special concepts how you can integrate heat pumps or use heat pumps. If you think about sector coupling, using excess power, for example, using low temperature heat sources, then you might accept lower COP as well. So you should be careful here if this is really a hard criteria, the COP of 4. Each heat source has its own characteristics. What do we mean with characteristics? That's the things we were talking before the break about the biomass boiler. Biomass boilers has certain limitations in load change rates. Biomass boilers are not able to be operated below a minimum load rate. They are not made for a lot of start-stops and standby and things like that. So this is what I mean with characteristics, and other heat sources have other characteristics. And all of these characteristics we have to take into account. They have to be considered in order to design an efficient system. And of course, the more heat sources you have, the more characteristics you have, the more complex is it to define a general operational strategy, to do a prioritization of the heat sources. Which heat sources should operate when? We call that merit order. So you have to define some kind of merit order depending on various parameters. These are economic parameters, of course. These can be ecologic parameters. This includes availability and the load demand itself. So the high complexity in load management, min-max load restrictions, of course, start-stop restrictions, load change gradients. I mentioned that availability. So other heat sources like thermal solar has their own characteristics in terms of availability. You cannot control that, for example, compared to biomass. Waste heat sources could be the same. And as I mentioned, we do not have much quality requirements for these alternative heat sources. I mean, you have general benchmarks, like I mentioned for the heat pumps, you have benchmarks for thermal solar as well. But here as well, it really depends on how you integrate a thermal solar plant. What is the task of the thermal solar plant? We have thermal solar plants with extremely high solar yields, specific solar yields, because they are just preheating cold water, for example, within a district heating system concept, or if you have a cold district heating system. So that's why I'm not a fan of having very hard-coded benchmarks for such systems anymore. It really depends on the application. More information in the planning guideline annexes, as we mentioned. This is an example of how such a system could look like. This is a simulated annual load duration curve. The system in that stage of enlargement has about 10 gigawatt hours of heat sale. It's still continuously growing, 6 production sites, 15 production units, and you see many different fuels and technologies used. This system was coming from a classical biomass district heating system and is now enlarged. So in the end, for this enlargement step, we will have, I think, only 5 production sites and maybe only 12 production units, not 15 as I simulated here. But it shows you the complexity of such a system. And now I want to come back to the question from Johanna. Johanna was asking, what are we doing in such a system, in a future system where we do not have biomass alone, but many other systems as well? How can we dimension the biomass boiler? Simple answer, you use the same criteria. You have this let's say we have a wood chip boiler. We have the same low load criteria, minimum daily average load should not, let's say, be lower than 25%. That is the main criteria of the mentioning of the boiler. And then you have to check how it fits into the system. If you have other heat sources and you get boilers or your dimensioning leads to a boiler to be operated below this low load criteria or with very low full load operating hours. That's the same. Actually, if you have very large boilers, then you run into trouble. This means you have to choose another setup. This means you have to choose a 2-boiler setup where you can maintain these design criteria and at the same time, as you see here, for example, relatively high utilization rates. Of course, they change because the system change, but this should be your main objective, that you do not integrate biomass boilers as peak load boilers. I saw concepts like this. I see people running around, even in Austria, saying, oh, biomass is very valuable, we should not use them for base load operation, we just should use them for peak load. But it's very clear that this cannot work because the investment is too expensive to use them as a peak load boiler. So for peak load, you have to find other solutions. What is really helping these new systems is this here. What you see here, there's no production. What does that mean? This is the storage tank. there is more production than we need actually. This is charging the storage, this is discharging the storage here. So storage capacities to balance the system become more and more important in order to allow a good dimensioning and good utilization of the boiler plants. But as a first approach, the same design criteria apply for the biomass boilers. You just use a single boiler, biomass boiler, or a two boiler plant, or in that case, it's two wood chip boilers here, and it's two pellets boilers here for this kind of system. Okay, Johanna, I hope that answered your question. Otherwise, ask again after my presentation, and then we can discuss it as well. Okay, so what you see here, large complexity. What you see here as well is the merit order, more or less. This is biogas production from wastewater treatment plant. This is a heat pump closely connected to this biogas source and wastewater as well. The thermal solar plants, of course, we cannot influence their availability. They have highest priority whenever they provide heat. The heat will be used, and these are the more controllable heat sources, so they have to be more flexible. But still, as we say, biomass boilers have limitations in terms of flexibility, so we still need to enlarge, in that case, significantly enlarge the storage capacities to have nice and smooth operation of the biomass boilers. Okay. Maybe I should mention here that the dimensioning of the boilers, it's a very tricky thing. What often is not considered, that we should not oversize our boilers, because we have other potential which we can use later on, for example, like integrating a flue gas condensation unit later on, integrating heat recovery with flue gas condensation and heat pump later on to enlarge the capacity. So maybe this is a very nice enlargement step. Of course, during the detailed design phase, you have consider some things to allow, to not have a lock-in effect, to allow these later enlargements. But there are many options to keep the operation of the boilers in the beginning nice and smooth, and have interesting options to enlarge it later on. Okay, but now I'm stopping, otherwise I'm going too far into detail, and I smash our time schedule. This is an overview of things you find in the planning guidelines. We provided, Christian put here a lot of things together to get an overview of what waste heat could mean, where you could find waste heat, some implementation examples. And at the same time, you see here, this is so widespread that you have very different types of characteristics of these waste heat sources. Coming to these characteristics, we try to sum it up as an example for waste heat as an example. I think waste heat is one of the most complex things. Of course, you have characteristics for heat pumps and thermal solar plants as well. But for the waste heat, I think you have the widest range. Where is the location? What type of waste heat source is it? What heat transfer medium is it? District heating people tend to think in water. It might be thermal oil, air, flue gas, what else? Steam, of course. So this is influencing the whole thing significantly. How is the location and distance in relation to the heating plant, if there is one at all? Temperature levels, daily, seasonal fluctuations in temperatures, in availability, in the capacity at all. So there are a lot of things to consider. For heat pumps especially, you have to consider worst case scenarios. We know, so this is going on here, the load characteristic, the load profile. We have very challenging load profiles. This is oftenly the reason why waste heat is not integrated. I know quite nice projects which could then not be realized because they have a very complex load profile. So you have waste heat from Monday to Friday and not on the weekend. On the other side, now we have nice examples where they cope with such challenges. They added large storage capacities. They connected the district heating network with another district heating network, classically with biomass district heating. So they have heat exchange within the systems to cover the weekends. So there are very, very nice solutions coming up for that. Operation interruptions as well, holiday shutdowns, very critical things. And expected future developments, for example. I mentioned that. Is sufficient space for the heat recovery in the industry available, for example. And one important point is a non-technical point from my point of view. It's not so easy to cope with industry. They have their own focus, they have their own standards. Often they are not interested in selling waste heat. That's not their main product. That does not bring a lot of income, but might bring a lot of problems to their production processes. So it's not so easy to start up such a project. However, these are the points we have to consider for the dimensioning of these plants to get a nice overall concept. Flue gas condensation is, from my point of view, state-of-the-art technology. It's proven, it's widely applied, not as much as I want it to be honest, for Austria. I'm responsible for quality management in Austria, and we still see many plants not even considering flue gas condensation. Sometimes it's not applicable, I know that, that's clear, but there is much more potential to increase the efficiency of biomass district heating plants, of biomass boilers. For QM, flue gas condensation is treated as just another heat source. Flue gas condensation is a bit special because you can closely connect it with the operation of the boiler, of course, but still it's just another heat source, like waste heat, for example. For QM, this is another heat source with its own characteristics. These characteristics may influence the dimensioning or the operation of the boiler, and you have to consider this. Okay, the efficiency and quality criteria for flue gas is relatively clear. You have to consider in the plant dimensioning, and for QM, it's still treated as standard hydraulic solution if you add a flue gas condensation unit. That's what we said in the past. Now I showed you more complex concepts in integrating heat pumps to increase the heat recovery rate of flue gas condensation use. Okay. QM and CHP. We mentioned CHP as a potential option for biomass district heating. Of course, CHP, very clear for me, very clear opinion. I have to say this is not an official statement from QM, but it's very clear in Austria that CHP is a base load source. CHP has to be a lot of full load operating hours in order to be economic feasibly and ecologically feasible. And at the same time, it's very clear that we need 100% of heat utilization of the waste heat or the excess heat of these CHP plants. Otherwise, you should not even think about building CHP plants. Again, it's considered as a heat source for the plant dimensioning, special characteristics, base loads, high priority, maybe lower flexibility, depends. You have to integrate it in the overall concept. We have standard hydraulic schemes coping with CHP as well. So you might want to choose a serial integration of a CHP plant, especially for an OSC, for example. But we do not have special quality criteria for the power production, like the ORC or steam turbines. QM as the Q requirements can be used likewise, that's very clear. As I mentioned before, if we start having more complex systems, we need more experienced planners, we need very good, highly skilled operators. So we see very bad examples with CHP plants in Austria, in Italy, in Switzerland, in Germany. So really take care. If you tend to go towards a CHP plant, really think of what you're doing. This is very costly in terms of investment and operation costs. And that's, again, take care here and try to find a very nice setup so that you can ensure a baseload operation of a CHP. Okay. Thermal solar plants, well-known technology. The integration of thermal solar plants in Austria started quite a long time ago. I think quite a lot of mistakes had been made as well, but we need to learn. That's like it is. The challenge is that the solar plant, which we cannot influence in terms of availability, must not force boilers being operated in start-stop operation or low load conditions. Everything we want to avoid with our QM planning process. So there is a clear suggestion. I hope Patrick can prove that the dimensioning of a thermal solar plant in the best case should be in a way to fully cover the summer operation, so that we do not need a biomass boiler, so that we do not need to have to start it up and down and stop it during the year. During the summer, or you have, as we mentioned, like a summer boiler, a small unit, a very flexible unit, then this could be a good interaction. But in general, you should not force a large wood chip boiler into low load conditions. In reality, it's clear dimensioning is often based on the available space on the roof, for example, on a storage building, whatever. So that might cause trouble, and you might not be able to fully cover some operation. But as I mentioned, then it is even more important to come back to the same basic criteria, how we want to operate our biomass boilers. And if this is not possible, you should think of integrating a small unit, automatic ignition, maybe it is even a pellet boiler, something like this. Or you have other options to charge your storage tanks during bad weather periods in summer. You should take care. Again, it's getting more complex. We need good storage management. Otherwise, the solar plant might not be able to deliver heat. We have very bad examples for that as well. Even more focus on low return temperatures, of course, a good hydraulic integration into the system. And what we see that we have interaction significantly differing specific solar yields, depending on the system temperatures, but depending on very bad integration of solar plants as well. Okay.
Harald?
Yes.
3 minutes left.
Oh, okay. I think that works out quite nicely, hopefully. Special plant configurations. Oh, well, maybe I'm too slow. Distributed heat sources. I mentioned that for the basic dimensioning, I don't care where these heat sources are. For the basic dimensioning of the sizes of the boilers, I don't mind if this boiler is somewhere else. For the hydraulic integration, the control strategy, things changes, of course. But this is standard nowadays. You can handle that. Different ownerships of plant and networks. That's no problem for QM. QM just clearly says, take care that you have interfaces, that you can optimize the overall system. Don't use it as an excuse that you have two different and both are not working efficiently. Large urban district heating systems. QM is not made for these large urban district heating systems. They are experts since many, many years. They have a lot of experience. They should know what they do. But still, sometimes have a closer look to some standards of QM, but because in terms of monitoring data acquisition, insulation standards of our small district heating plant, we are often much better than the larger ones. For a biomass plant integration, use QM likewise, maybe not for the whole production units, if you have large power plants, that does not make sense. But for the boiler and biomass boiler plant, you can use it likewise. Biomass boiler feeding into a large urban district heating system. PTUI, hopefully they will build their biomass boiler. I'm waiting for that. We have a nice plant in Graz. There, this is a perfect example for how we can apply a single boiler plant without storage, because we have a super large heat sink, and whatever we produce, we feed into the district heating network. Then, of course, we do not need a storage tank. Then we have a single boiler plant, but this is totally different strategy here. But you can, of course, apply QM for the boiler plant. And for non-space heating processes, industrial processes, it's actually the same. We do not want to force our boilers into an operation which they are not able to cover nicely. We see biomass steam boiler plants operating from Monday to Friday and have no heat demand on weekends. That's not possible for a 5 megawatt boiler. So you cannot stop it for 2 days and restart it then. You have to consider this. Otherwise, you can apply QM for that as well. Okay, last slide. So the standardization of multi-fuel technology systems is limited, as stated here. I tried to work that out, that we have so many different options and concepts that it is getting harder and harder to come up with very, very detailed design criteria, quality criteria. So you have to change the mindset a little bit and use QM likewise. So that you have the same idea of QM, detailed, clear planning procedure, good structured, clear tasks and responsibilities, and the same criteria for a biomass boiler, for example, but for other heat sources as well. They just have other criteria. We want an overall efficient system. We want to operate all units within this design criteria. Okay. That's it. I hope I could bring you a bit closer to that topic as well, and happy to answer your questions. Thank you very much.
Thank you, Harald. Are there any questions? If there are not very urgent questions now, I would suggest to make the discussion after the next presentation. And go now directly into the next presentation of Harald Blazek, who will be our next speaker and our last speaker for today. Harald Blazek is a pioneer for absorption heat pumps. He's working in the company StepsAhead Energy Systems and was also one of the founders of the company. His presentation will be about absorption heat pumps for biomass district heating and also about waste heat utilization. He will talk about the basics of absorption heat pumps, about applications and potentials, and will also show some best practice examples. Harald Blazek, it's your turn now. You can start.
Thank you for the nice introduction. And just let me start my clock so that I don't miss the timeline of not exceeding the timeline. Thank you for the possibility for presenting the topic of absorption heat pumps. It's a topic where I'm really intensively working on, and where I would also say it's not only the brain, it's also the heart. I want to push the knowledge that more people see what is in this technology. Looking, I guess you see my screen. Can I have a short confirmation, please?
Yes. Yes, everything okay.
Thank you, fine. Giving a short overview, I will introduce the company with one slide and then directly jump into the different topics. And the biggest part of the presentation will be the project examples. So who is StepsAhead? Who are the founders? You see them on the picture. The right side, that's me. The left side in the picture, this is Michael. And actually, we are standing in front of 4 absorption heat pumps having a heating capacity of 150 megawatt in absorption energy, in delivering hot water from absorption heat pump in a combined heat and power plant. This shows us already that the topic is much, much larger than it is perceived in Europe usually. We will see this during the rest of the presentation. What is StepsAhead doing? Well, I don't want to read down the text that you have on the slide. What we do is we understand these machines, we calculate the machines, we calculate and simulate the projects, and we take care that projects in Europe using absorption machines work well and deliver as predicted. So what is an absorption heat pump? How does an absorption heat pump work? I will not become too technical, too far in the detail, but we should have a basic understanding of the process. And for starting that, let us look in the evaporator. This is the point where the machine accepts the input of low temperature heat, the cold side of the process. When I want to cool down this external heat exchanger, actually one question more, do you see my mouse?
Yes, we do.
Thank you. When you want to cool down this heat exchanger to 25 degrees C, you will need on the inside of the machine a boiling temperature of water at 24 degrees C, colder than the heat exchanger. This defines me, this machine is working in vacuum. The water that runs over this heat exchanger boils inside because of the low pressure, and by that it is very effectively cooling the external circuit. But I am running into a difficulty, a problem. The more and more steam I produce, the higher the pressure gets within this chamber. And considering compression chillers, compression heat pumps, they suck out the vapor and compress it. An absorption heat pump uses highly concentrated salt solution or any other matter that is attractive to the humidity for bringing the steam back to liquid phase. Evaporation of steam is cooling. Pressure rises due to the amount of steam. No, pressure is kept constant due to the irrigation of a highly concentrated salt solution. We use more than 60% salt content in most of our projects. The result of this project, I get a diluted solution, salt solution with too much water in it. And so consider yourself what you do in the kitchen. When something is not salty enough, you boil it up, you add heat, bring out the water that was too much, and you get back concentrated salt solution and you get back pure water, which is needed for running the process continuously. As we are working on other temperatures in the upper chambers of this machine, we're also working on a higher pressure level here. I don't want to introduce it more than this. If you should have detailed questions, we will have time after the presentation. Now to absorption chillers. They are much better known than absorption heat pumps, and in basic terms, they are absolutely the same. When you sell the cold side, you call such a machine a chiller. When you sell the hot side, you call such a machine a heat pump. But the machine itself remains the same. It just operates on different temperatures, on different pressure levels. What's the economic benefit of a heat pump versus a chiller? Let's have a look on that. I am driving an absorption heat pump with 1 megawatt of heat. By that, I can accept 0.7 megawatt of low temperature waste heat. And my benefit from this machine is 1.7 megawatt of useful heat. When I do this with a boiler, I must burn fuel, gas, biomass, oil, whatever, for 1.9 megawatt approximately. Comparing this to a chiller, I'm driving the same machine with heat of 1 megawatt. My cooling capacity is then only 0.7 megawatt. And when I want to produce this cooling capacity with an electric chiller, I need something like 140, 150 kilowatt only in form of electricity. Cutting a long story short, the difference in the economic benefit between a heat pump and the chiller is usually 10 times more at the heat pump. This brings us to the result that heat pump projects, they're usually always profitable when you can find good candidates for. For chillers, you only can operate single-stage chillers when the energy the driving energy is for free. Sometimes you have heat that is not used otherwise, or when the heat is very, very low priced. 15 euro per megawatt hour, that's 1.5 cents per kilowatt hour. A long text slide, and I continue immediately. This is the explanation of the machine. You can read it when you download the files. The file will be available by the organizers of the ENTRAIN workshop. Looking on the machine itself, is such a machine complicated? I would say no. The machine is a combination of 4 tube and shell heat exchangers, of 1 plate heat exchanger, and a couple of pumps, a couple of valves, but mainly the machine is a big amount of steel, similar to a boiler, similar to a normal heat exchanger, whatever you are used to. In the calculation, it can be a little bit tricky when you simulate the machines, because you must be able to calculate the lithium bromide process, the absorption process with the salt. But in operation, it's in basic terms a simple machine. We are coming to the project examples. And I'm starting with a biomass project that we have commissioned last year. We have now more than 1 year of operation. And this biomass plant in Wagrain in Salzburg in Austria, it is probably at the moment the most efficient biomass plant that exists in Austria, due to the very low temperatures for the flue gas condensation. In standard operation at the nominal load, we have a cold water temperature for the flue gas condensation of 22 degrees. In part load operation, we even reached cold water temperatures of 15 degrees C. And the owner has told us before Christmas last year, hey, we had a weekend where the flue gas system brought almost 50% of the boiler capacity in addition. How is this possible? They had a very, very wet fuel with a water content between 55% of water, 60% of water. And when you have so high water contents, you can have 50% additional energy from the flue gas system, consisting of economizer and of condensation, of the condensation heat exchanger. Update for this client. The client is Navia After having ordered the machine in Wagrain, the client placed 2 additional orders, and 2 of them for, one of them for 2021, the second one for next year. And you will see some data of one of the projects in the next slides. First, the basic schematic, how such a machine is integrated. Typically, when we have 1 boiler, we use a boiler at 150 degrees C. When we have 2 boilers, a big one and a small one, we have the small boiler on 150 degrees C. And actually, but this is not yet officially published, we are working on biomass solutions for boilers operating at only 105 degrees C. This also allows a good flue gas condensation, but not as good as with a higher temperature. Yeah, back to the fuel efficiency. The fuel efficiency of this system in Wagrain reaches 116% of the lower calorific value. I guess that's not a bad value for a biomass heating plant. Project history of this project in Wagrain, only in a few slides, just to give you an idea of the situation. You have to start with the designers of the machine, and this is in China where the machines are produced. We are in a meeting with our engineers. You need to have a full simulation of the whole heating plant, including the heat pump and the flue gas system. You need all specifications. You need to check the design. You need to check the manufacturing. You have quality procedures for all welding, etc., etc. And at the end of the day, you have a machine that is ready for shipping. One slide more. No, even one, this is on the test bench where the in-factory test is done. This is ready for shipping. And this is a happy client at the end of the project, just after bringing in the machine in the heating plant. Next project, this is the one I mentioned for the same client, but in south of Styria, in Stras. The delivery of this machine will be next Friday. So it was very convenient that we have our presentation today, and a few days later we bring out the next machine. This size is somewhat smaller. The Wagrain machine had 0.8 megawatt in flue gas condensation capacity. This one has 0.5. Switching to a larger project, this is a big biomass power plant. The boiler capacity of this plant is 50 megawatts, 50, and the capacity for flue gas condensation of this system is 10 megawatt, meaning 10 megawatt of additional harvest for energy that otherwise escapes through the chimney. This machine had cost something like a little above 1 million. And the savings per year are also 1 million. For the smaller biomass plants, the numbers don't look that nice, but still they look usually much, much better than the payback period for the boiler and the whole biomass plant itself. Yeah, the client in Klagenfurt, he has 3 sites in total, and 2 of them are already equipped with such an absorption machine. The third one might follow later. Let's see how district heating consumption in Klagenfurt will further develop. We make a big jump over to another continent and we look to China. This is an example that was very impressive for me, and I simply did not understand why we don't see this in Europe. We have a coal-fired power plant in this case, whatever the fire comes from, but we have a boiler. The boiler is producing steam, and our way in Europe, in the old conventional style, was take steam from the turbine, put it on a heat exchanger, and produce hot water for district heating for the city. And in China, they make it much smarter than that. They use the steam for driving the absorption heat pump, the AHP. They take for 1 megawatt of steam, 0.7 megawatt, 70% additional free energy from waste heat, and they deliver 1.7 megawatt to the city. This is 70% more output from the same driving energy. And in Europe, we don't see that. I must say that clear because China does it since 2010. Already more than 200 machines of that style installed in project sizes that are really huge for the big cities. And we only need to fly there. We only need to listen, and we can do the same in Europe as well. I think it's one of the big points where we have to go for reaching big targets. How does it look like? This is a picture where one machine is combined, the lower half of the body and the upper part, just mounted by the crane. A little bit later, you have 4 machines. A little bit later, you have 8 machines on one place, and you have a 300 megawatt district heating project that needs 40% less energy compared to a European project of that size. Looking to bigger machines, but it will not become bigger than this one. This was the biggest worldwide in 2018. Today, the biggest machine is similar in size and has 90 megawatt in one machine. This is already pretty impressive. Cannot be transported on European roads, but can be transported when you are on the coastline or on a river or a canal, if you can transport it by ship. Coming back to smaller projects, looking to industry, looking to waste heat usage. Sometimes you can use that for, you can do waste heat projects for optimizing the industrial process itself. So the energy for driving the absorption machine comes from the industry, and the energy delivered is used in the industry. This is an example from a big brick producer, and they need to dry the freshly pressed bricks, the green parts, then they burn it in the kiln, and from the kiln they have the waste heat. It's an ideal combination. Before having installed this machine, they needed natural gas as additional heat for the drying process. After the integration of the absorption heat pump, they did not need natural gas for the drying process anymore. The drying process is entirely fed by the waste heat of the kiln, of the burning process for the in the production of the bricks. Yes, this client as well. He has a couple of new projects going on, but it's too early to talk about in detail. Jumping to the next one. This is already an old project dating back to 2015, 2016. This is in Tyrol in Austria. And the project was on a place where they produce these iron cast or steel cast pipes. And when melting the steel, they have a high temperature waste heat from the melting oven. And they had already in the past a heat exchanger that was capturing from this more than 1,000 degree gas, 170 degree hot water. And via a heat exchanger, they harvested from the flue gas. They harvested 3.5 megawatt. They sent these 3.5 megawatt to a heat exchanger and delivered 3.5 megawatt district heating. The absorption machine can ameliorate this process a lot. The 170 degree C can be excellently used as driving energy for the absorption machine. Waste heat from cooling towers can be integrated in the process, and with 3.5 megawatt driving energy and 2.5 megawatt from waste heat, you can deliver 6 megawatt to the grid, which is again an increase by 70%. 70% more energy harvest from the same sources. The next new project commissioning will be in January. In December 2021, we will bring the machine. In January, we will do the commissioning. And you see a steel structure, 12 meter high. Up there, this is the room where the machine will be placed into. The machine is split to do two different parts because the room was so small and the machine is big. And the height is even not the only difficulty in this project. It is a machine with 7 megawatt heating capacity. The difficulty or the interesting point is the crane position. Here is the location for the heat pump in the circle, in the round circle. And on the other side of the building, almost 40 meter apart, is a position for the crane. And the heavy part has, I think, something like 30 tons. And it's not so, let's say in simple words, it will need a big crane. It will need a very big crane so that you can transport 30 tons over such a distance. Pictures will be in the next presentations by next year. So the next type of machine. This is also an interesting one, because sometimes you have locations where you need 90-degree hot water, maybe for district heating, maybe for another use, and you have a waste heat of 20, 30, 40 degrees C, but you need 90. And with an absorption machine, you can drive the absorption machine from a fuel or from hot water or from steam or whatever, integrate the waste heat. And when you consider this now as a boiler, from the gas input that I have in this picture, I have 155% of fuel efficiency when considering that my output will be 17 megawatt. 10 megawatt is the heat from gas, 7 megawatt is the heat from the low temperature source. And interestingly, if the waste heat source is not always available, if you use an electric heat pump for using a low temperature source, and the low temperature source is interrupted, is not permanently available, the electric heat pump cannot deliver. In the time when the waste heat is not available, this machine, this absorption heat pump, can work as a standard boiler and still deliver the 90 degrees C you need. Coming to the next type of machine. This again is an Asian project. Let me zoom in a little bit here. These are the district heating pipes, diameter 1,400, 1.4 meters each pipe. 4 of these pipes laying in the ground. And the interesting is actually not that we have 8 tons per second mass flow. The interesting point is the return temperature of the district heating grid. Is there anyone who has a fantasy, who has an idea, how the hell can you cool down a district heating return to 20 degrees C? What is the consumer on the other side? And the answer is, again, an absorption machine. I still show it as a standard heat exchanger. I have energy input from the left, 1 megawatt. I have energy output on the right of 1 megawatt. But the interesting point is already marked. Usually, when this is a normal heat exchanger, 38 return at the consumer is best case 40 degrees C, not 30. Now I must lift the blanket. We must look into the machine. The process actually is a simple process. It is a standard absorption machine as you know it, combined with a standard heat exchanger. And as driving energy, the driving energy comes in this example with 115 degrees C. It drives the generator of this absorption machine. Then it is led to the standard heat exchanger, having a little bit more than 100 degrees here. Here it is cooled down to the temperature that you would normally reach, 38 return flow, 40, 40.5 in this case. And this is cooled down in the evaporator, and the return flow goes to 30 degrees C. 10 degrees less or more than 10 degrees less in this example. Other projects have 20 degrees less. It always depends on the temperatures. The bigger the difference between high temperature on the driving side to high temperature on the consumer side, this is the energy capacity that you can use for driving an absorption heat exchanger. And let us make numbers out of that. This is my hometown Graz. This is an industrial site, 12 kilometer with a 12-kilometer district heating pipe between the connection to the city's grid and to the industry. And when you want to increase the capacity of this piping, you can install here on the right side in the city such an absorption heat exchanger. And depending on the different temperatures you have, you are able to deliver 118 degrees in the coldest times. In this case, we can reduce the return temperature only by 2.3 degrees C. When we have to deliver 80 degrees C in the city, we can reduce the return temperature by 20 degrees almost. Again, detailed questions to this. Our time is now limited. I must have a look on my time budget. Detailed questions can be discussed after the presentation itself. A more complicated machine, not 4 chambers, but 6 chambers. And 2 of them, 1 evaporator and 1 absorber in only an internal circuit. I'm cutting a long story short. This is a special machine when you want to deliver on the hot side interesting district heating temperatures, while reaching on the cold side 10 degrees C. This can be used for delivering cooling to buildings and heating to heating circuits at the same time, or cooling to industrial processes. Switching to the next one. I have from an industrial production site a waste heat source from 60 degrees C hot water, which I can cool down to 50 degrees C. And this energy is the driving energy for my absorption machine. The type of absorption machine is sometimes called heat transformer, sometimes it is called category 2 heat pump. And the interesting point is driving energy on 50 degrees C, energy delivered on 90. How is that possible? You cannot operate a heat pump with a lower exergy source, bringing the energy to a higher level. And okay, in fact, it is possible when you look on the related power. We have an input of this 60-50 degrees C water circuit of 6.2 megawatt, and a little bit more, 52%, are discarded on a cooling tower. And when I discard at 12 degrees C, a little bit more than half of the energy that I has as input, then I can deliver the other half as useful energy to the consumer. And interesting is, I don't need any steam as driving energy. I don't need electricity. Yes, okay, I need a little bit of electricity for these pumps and for the cooling tower, but including the cooling tower, this is 2%, 3%, 4% of the energy delivered. This is almost nothing compared to the harvest that you can reach with such a machine. Coming to the next example, we are looking on cogeneration, on trigeneration. And in this case, I'm looking on gas engines. Can be biogas, can be natural gas. And typically, when you consume in cogeneration the heating, you bring all heat flows of these engines to a 90 degrees C or 100 degrees C level, and you send it to the consumer. When delivering cooling from such a project, then you deliver 100 degree water in standard setup, 100 degree water to a single stage chiller, and you deliver and you get from 1 megawatt of heat, you will get 0.7 megawatt of cooling capacity. And this can be made better when you make a slightly more complicated absorption machine shown in the right picture. Then you get for 1 megawatt of energy combined in form of hot flue gas and combined in form of 100 degree hot liquids. Then you can get 1 megawatt of cooling for 1 megawatt of driving energy. And this is 40% more cooling output, while the engine runs exactly in the same way as before. Looking in wintertime almost nobody needs cooling, but in wintertime heating is needed. And when you have such a gas engine, and you have a heat pump with this high temperature generator in special form, then you can increase the heat input by 20%, and you can reach fuel efficiencies of more than 100 with a cogeneration system. The low temperature input in this case comes from flue gas condensation from the engine. We're coming more and more to the end of this presentation, or to the final slides, and it gets a little bit more technical again. I want to share with you some benchmarks about absorption heat pumps so that you can consider yourself, is it a valuable project? Does it make sense for me? Yes or no? And looking again in an absorption heat pump, looking on the temperatures. What is, in a district heating application, the temperature that is set at first time, set immediately by the grid? This is the return temperature. This one you cannot change, or changing this temperature is a long and exhausting process. This return temperature, actually, this defines what cold water temperature I can reach for the flue gas condensation. And 30 Kelvin difference from 55 to 25 is a typical value. Usually you have 25 to 30 Kelvin between district heating return and cold water output for the flue gas condensation. Important first benchmark. Temperature increase by the heat pump. When I go from 55 only to 65, then I can reach 22, 21 maybe. When I go from 55 to 80, then I have this benchmark with the 30 Kelvin. And this is a very typical value. The heat pump increases the return temperature to 80 degrees C, and then the boiler is used for heating to 90, to 95, to 100, 110, how much you need. When the low temperature heat source that you have is very warm, is in the range of 50 degrees C, then you can directly go to 100 degrees C with a single stage absorption heat pump. Oops. Heat from the boiler needed for reaching target value. I mentioned this already. And last of the benchmarks in this slide, there is a maximum temperature that absorption heat pumps shall not exceed. And this is due to the corrosion inhibitor this is used. The machine shall in the generator not be warmer than 160 degrees C. And therefore, we will reach 100 here when the source is warm, but usually we will not reach significantly more than 100 with this machine type. Coming to the design criteria for a machine, what is the difficulty in the design, or what is a bit tricky, what needs calculation? We mentioned already that we have roughly 30 Kelvin on between the lower chambers, and this means that the salt solution that absorbs the steam in this chamber, it has a concentration on maximum on 63%. 63% salt, only 37% of water. This high concentration allows me to separate these two temperatures as far as possible to bring 30 Kelvin difference. Now looking on the upper chamber, here I have in principle the same picture as below. I want to reach high temperatures, and here I have my salty circuit, here I have my clean water circuit, and this means here I want to have the salt concentration as low as possible. And within this dilemma, the designer of the heat pump has to decide which is the best way to go.
Mr. Blazek,
yeah.
3 minutes, is it okay?
Actually, I have, according to mine, I have more, but I will speed up. I will need a little bit more.
It's no problem, no problem.
Okay, thank you. These salt concentrations, etc., can be shown in the diagram. You find it in the download area of our website. And the last point, how to develop successful projects. Let us recapture, let us rethink the projects. Waste heat usage in this industrial project, the driving energy was for free. The big power plants, the driving energy was not absolutely for free, but the same driving energy brought 70% more output. Biomass plant, the driving energy was for free. Cogeneration, driving energy was for free. You don't pay any additional heat bill. And these are the smart projects that you should chase, that you should search. These projects are always economical with absorption heat pumps, and payback periods can be really, really short. What do you need for being sure that your project will be successful? You have seen this photo for the full project, photos for the full project cycle, but looking on the most important points of it. You have to have a good and full simulation of the absorption machine. This is a machine as it is calculated by StepsAhead already 3 years ago, more than 3 years ago, okay? And you have as well, you have to simulate the full system. This again is a biomass heating plant with a one boiler system. And only if you do both, then you can be sure that you will have trusted economical data for an economic decision, and that the supplier of the boiler will know what he needs for delivering the right boiler, and the supplier of the flue gas system will know what the flue gas system must be able to. Thank you for that. I think that's it. And I have even finished in time, as it seems. Oh, ready for any questions?
Very great. Thank you.
I give back to you.
Thank you very much, Harald Blazek. It was a very interesting input about absorption heat pumps. It's good to see that there are already so many different and so nice working best practice plans existing. And for me, it was very fascinating how much efficiency increase can be reached by such applications. As we also heard before in Harald's presentation, using waste heat and also other renewable energy, then biomass is a very complex challenge, but will be more and more important in the future.
I don't want to see that we have two questions in the chat.
Yes, I want, yeah, great.
Shall I directly answer these questions?
Yes, maybe we can read it before.
Yeah, Torvald Harald is placing a question. It's already the third Harald we have today. Hello.
Yes.
When you have too much heat in summertime, seasonal storage is always an interesting point to consider, but you must be honest, the seasonal storage has in its storage volume only one load change per year, meaning you heat up in summertime, you cool down in wintertime, and it needs to be really, really large, more, let's say 10,000s of cubic meter of storage volume, so that the specific cost per cubic meter of storage is sufficiently low. Examples exist already for many years in Denmark. Yes, it is an option to go for seasonal storage, and Danish system having these storage volumes, as Danish system have very low return temperatures in the district heating grids, often 40 degrees C, 30 degrees C, they can manage their storages for a high temperature spread from 30 to 90. Austrian projects, they have a district heating return of 50 or even 60 degree or even warmer. In that case, you will need a heat pump, either electrically driven or absorption heat pump, for bringing down the temperature of the seasonal storage. This question is a good topic for a workshop on its own. We can talk a lot about that, And StepsAhead was so far involved in 3 projects developing such storages and considering how to run the heat pump. The details we must postpone to a later date. The basic answer is yes, it is for sure. When the heat source is big enough, it is a good option.
Mm-hmm.
Harald, can you live with this answer?
I think you can.
Yes, sure.
Okay.
I can. Thanks a lot.
Okay, switching to Matteo Mazzolini. Actually, the maintenance is typically something like 1–3% of the capital invest per year. And if it is 1–3%, depends on the size of the project. The electricity consumption of an absorption heat pump is usually less than 0.5% of the flue gas condensation capacity of the cold side. So the electricity consumption is more or less zero. And the cost for maintenance, standard maintenance, is a weekly check of the vacuum pump, which is just you walk by, you look at the pump, you see how is the level of the oil, and not more than the visual check. And if oil is needed, you add oil. If condensated water is in the pump, you empty this. And usually twice per year, you should take a sample of the salt solution, meaning by help of an external vacuum pump. This is the way how we do it. We take out 0.5 liter of the salt solution and we send this to the laboratory for testing, and the result will tell us about corrosion of the solution inside the machine. It will give us information about the acidity or the alkalinity in the machine. It will give us the information what is going on in the machine. And usually after a period of 2 years, 3 years, you start that you have to refill some 2 liters of acid or some 1 liter of caustic liquid for bringing the machine back in balance. And I would say when the machine is not far away, maintenance is a question of less than 5 days. If it's a question of 2 or 3 days on site, and travel times come on top. When the travel takes a day on its own, then you have to add these times.
Thank you.
Do you provide full service maintenance contracts? Yes, we do. And we also can consider sale of energy projects when the project is financially trustable, so that a bank takes this financial risk, and when the project is financially sufficiently attractive. How long does it take for the salt solution before being substituted? The oldest machine I know is 70 years old and it runs on the same solution. Solution is typically maintained but not exchanged.
Mm-hmm.
Are there any other questions?
Maybe also for the presentations before or the presentation before.
I have another question, Harald. As a plant operator or a planner, being not so experienced with absorption heat pumps, how do I find out if such a project could be feasible for my plant?
Actually, the first question, and I go beyond biomass in the first answer. The first question is, do I have a situation where I have a low temperature waste heat source and a warmer driving energy? If I have this combination, it is a good idea to check further. And for a first check, it is the simplest point to write an email to office@StepsAhead. I am the CEO, I get this email, Michael is the CTO. He gets this mail and we will take care of it. And when looking in biomass projects as the focus of this event today, when you have very dry biomass, when you work with pellets, okay, then the potential is limited, then it's only 10, 12% that you can get from flue gas condensation. When you are working on wood chips and you have 30% water content, 30, 40, more than 40% water content, the more humidity you have in the fuel, the more water you will have in the flue gas. And the more water you have in the flue gas, the better the project. Waste incineration can be, where garbage is burned, can be a very good option for installing a heat pump for the flue gas system. And as you said already, Harald, is it possible to build flue gas condensation systems that withstand, that hold in a daily operation? Yes, there are dozens of systems existing all over Europe by well-known manufacturers. This is something where there is no doubt behind.
Thank you very much. Yeah, if there are no more questions, or if any questions comes out later, just come back to Harald and Christian, and also to me. We can also forward the questions concerning the last presentation to Mr. Blazek, or you can write him an email directly.